grade 10s and welcome to this week's lesson where we're going to prepare for your paper 2 content. Now you're coming up to exams if you haven't started writing them already, and that means you're either going to write one big exam with all of the content in, or two smaller exams where we've got paper 1 content in the one and paper 2 content in the other. Now, I like to think of paper 1 content that is everything that has an X, so all of your algebra, your algebraic functions, your equations, inequalities, all of those things. Today's lesson, we're going to focus on the content that's in paper 2. Now, paper 2 content includes trigonometry, Euclidean geometry, analytical geometry, if you've done it, and statistics, if you've done it. So, at the end of the year, paper 2 will include all of those, but for now, it's only going to include those topics that you've already done. There's going to be quite a lot of notes at the beginning of this lesson, so I want you to have your pen and your paper ready and take down key points as we go through. Think of this as really a cramming session for you to put down all of the knowledge that you need for the exam. After we've done a bit of cramming and written down all of the notes, we're going to take a look at some of the challenge questions from previous shows. So especially those ones from the Euclidean geometry show. And do you remember how to do trigonometric functions? It has been a while, hasn't it? Well, we'll go over those as well. Shall we begin? Okay, so let's take a look at our slides. And the first one tells us what's in paper 1 and what's in paper 2. So we have got, and let's just get a nice color, in paper 1 we've got everything with the X, algebraic expressions, exponents, number patterns, equations and inequalities and functions. But today we're focusing on trigonometry, trigonometric functions, and Euclidean geometry. Okay, key concepts. Two angles whose sum are called complementary angles. Now this is something we don't usually talk about, but it is important. Now sum means that they add up to 90 degrees, well, sum means that they add up, and 90 degrees means that they add up to 90 degrees. So those two might not be touching each other, but they are still complementary. It's not something we really use very often. And here we have quite a strange example because these two are vertically opposite from each other, but they're also complementary. Okay, now that we've written down this word, complementary, let's go on to the one that we use a lot more, which is supplementary. Now when two angles are next to each other on the same straight line, so there's our straight line, and there are two angles. We call these supplementary adjacent angles. And you'll notice how I am abbreviating everything. It's nice to abbreviate, it means you don't have to learn the spelling. So supplementary adjacent angles basically means there are angles on a straight line that will add up to 180 degrees. In other words, they have a sum of 180 degrees. And there it says, two angles whose sum are 180 degrees. Maybe that 2 is a bit misleading because it could be more than 2 angles. We could have another angle over there and they would all add up. The whole section would add up to 180 degrees. So it's any angles that form a straight line when you do them. Now vertically opposite angles, and you'll remember I asked you to hold up your fingers and make them bigger and smaller to illustrate how vertically opposite angles are exactly the same size. So angle 1 is equals to angle 3, and the reason you would give for that is that they are vertically opposite angles. Once again, pay attention to the lack of words I'm writing down. Maths is not about writing paragraphs. It's just about explaining yourself in the shortest possible way. So vertically opposite angles are equal is a perfect way to write down why 1 and 3 are equal to each other. Looks kind of like a guy with glasses. There we go. Okay, a little bit of fun. And now let's go on to parallel lines and transversals. A line that cuts two lines is called a transversal. When a transversal cuts two parallel lines, certain relationships are formed between the angles between the lines. Okay, so we have two important points here. Firstly, that any line that goes through two lines is called a transversal. So that one over there is called a transversal. Oh, let's spell it right. Versal. But there are no fancy relationships over here. Nothing is equals to anything else. Why? Because these lines are not parallel to each other. However, these lines are parallel to each other. So these relationships are formed. Shall we go and see what are formed? Over here we have the F shape. Now I like to remember, because I'm terrible at remembering, I like to remember them as this. You see how the two R's on top of each other look kind of like an F? Which is the only word that's spelt with two R's? Corresponding. Corresponding angles, can you remember if they are equal or supplementary? Corresponding angles are equal. And that's pretty important to remember. So, in order to use that though, we need to state which lines are parallel. So let's say we're talking about angle 4 and angle 8. We would say, as our statement, angle 4 is equals to angle 8, and then our reason would be corresponding angles, and notice I'm abbreviating, but it's really, really important that we also state which lines are parallel. Otherwise, it'll just be one of these rubbish diagrams that we have at the top that I've scribbled all over. Look, scribbling again. So, we need to state that AB is parallel to CD. Otherwise, the corresponding angles would not be equal. Okay, this next one, can you see what kind of shape it forms? It almost looks like an N. Let's draw an N over here. I remember this by going alternate. Do you see the big N in the middle? That helps me to remember what shape are alternate angles. Now in this case, it's angle 4 and angle 6 that are alternate to each other. And if we think about it, angle 6 is vertically opposite to angle 8, which means that angle 6 is equals to angle 8, which therefore means that angle 4 has the same value as angle 6. But if we wanted to skip out the step where we would say angle 6 is equals to angle 8 because of vertically opposite angles, blah, 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 we could just jump to here and not do this, and we could just write down alternate angles. But once again, we have to state which lines are parallel to each other, otherwise the reason just doesn't make sense. Now, if alternate angles are equal and corresponding angles are equal, then co-interior angles with the C shape are the ones that are supplementary. And look how I write co-interior. Co-interior. So once again, I'm using the shape of the word co-interior to help me remember what shape I'm looking for. Now, co-interior angles are supplementary. Do you remember what supplementary means? It means that they add up to 180 degrees. So in this case, I would say angle 4 plus angle 5 is equals to 180 degrees. Why? Because they are co-interior angles. And that means nothing until I've said which lines are parallel to each other. Sure, grade 10s, how are you feeling? You okay so far? We're going to go to the next slide now, but I want you to just sit up straight. We've discussed a lot. You ready? Okay, let's go back. And now we'll just wait. Types of triangles. When each angle and side are different in size, the triangle is classified as scalene. So those triangles will look like any kind of weird random triangle. There's nothing too exciting about any of those. When a triangle has two sides that are equal, the two base angles will also be equal. Can you remember what these are called? They're called isosceles triangles, and those are actually really useful because if we know that those two sides are equal, we know that those two angles are equal, and then it makes our life easier. Equilateral triangles. Now you see that equal looks kind of like the word equal. And of course, equilateral triangles have three sides that are equal in length, and each angle is equals to 60 degrees. Now, those are three different definitions by themselves, three different types. Then we also have acute triangles, but acute triangles can also be scalene, or they could be isosceles, or they could be equilateral. So it could be an acute equilateral triangle, but acute angle triangles only have angles of less than 90 degrees. When one of the angles is greater than 90 degrees, so greater than 90 degrees, we classify the triangle as obtuse. You'll remember an obtuse angle is anything that is more than 90 degrees. And a right-angled triangle is wonderful because it means we can use trigonometry and Pythagoras, so trig and Pythag. A right-angled triangle is one that has a right angle in it. Okay, then we've got similarity and congruency. Now similarity, I prefer just to think of as three angles are the same size. It's just easier to prove, but most of what you're doing in congruency, or most of what you do is what you need. You need congruency for most of what you do. Geometric figures are congruent if they have the same shape and the same size. This means that all the corresponding sides and corresponding angles are equal to each other. There are four conditions for showing that two triangles are congruent. The first one is three corresponding sides are equal. So we would need to prove that three sides have the same length as another three sides. The second one says two corresponding sides and the included angle are equal. So we would look at a triangle and we would try and prove that in our two triangles, that side is equals to that side and then that angle over there. It has to be side, angle, side. It must be that. Can't be anything else. Then, two angles and one side are equal. That's side, angle, angle. And in a right-angled triangle, the hypotenuse and one of the other sides are equal. Okay, now grade 10s, you'll remember that I've said over and over and over again that mathematicians are lazy, and congruency just shows how lazy they are. You see, they don't want to prove that every single side is equals to every single other side. And they don't want to prove that every single angle is equals to every single other angle. It's just going to take too long. So they find shortcuts, and the 4 cases of congruency are exactly that. They're shortcuts that the mathematicians have taken, which tell them automatically if a triangle is congruent to another one. So if they can prove that the 3 sides are equal, then it's automatically going to be congruent, because there's no way you'd be able to draw another triangle with the same 3 lengths of sides and not have the angles be the same. Now the same with the 2 sides and the included angle. Once you have the measurements of 2 sides and you prove that they're the same as another 2, and you've got the included angle, there is just no way those triangles could be different. You can't draw them any differently. Then you have side angle side, and, well, side angle angle at least, because we just spoke about sides angle side, and then you've got the right angle hypotenuse side. Okay, we're not finished with the notes yet, but I don't know about you, I really need a break, and then we'll come back. We'll see you just now. Okay, grade 10s, welcome back. I'm feeling a lot more calm now. I've taken a moment to recenter myself, and I'm sure you have as well. We've still got quite a few notes to go through, and I'm going to try to go through them as quickly as possible because I really want to get to the exciting maths. And maths is exciting. Okay, so let's go back to the slides. Now, the next thing we need to talk about is probably the only new thing that you learned this year in Euclidean geometry, the midpoint theorem. Now, this is the proof picture if we wanted to prove it, and it's important that you know how to prove it. But what I really want to emphasize at this point, that if these 2 lines are parallel, and if that side is bisected by this line, and this side is also bisected by this line, then this line, ED, will be half the size of AB. Okay, so there's quite a lot of information there. We've got to remember that the midpoint or the mid-segment is formed by a line that cuts through from one midpoint to the other midpoint. And if a line is automatically drawn through those midpoints, it will automatically be parallel to the bottom line. And if it is in the midpoints, it is also half the size of the base of the triangle. Okay, so don't forget to go over that proof later. Now, we learned about a whole lot of quadrilaterals. First one was a parallelogram, where both opposite sides are parallel, both pairs of opposite sides are equal in length, both pairs of opposite angles are equal, and both diagonals bisect each other. And you'll remember that we spoke about a squashed rectangle. So here's our rectangle, and then we squashed it to get there. Can you remember how to remember the changes that happened? When we squashed it, the diagonals went from being equal to each other to just bisecting each other. Okay, let's go to the next one. Properties of a rectangle, and here we go. You'll see that the diagonals are all equal to each other, but they also bisect each other. There's some right angles, and the opposite sides are equal. So both pairs of opposite sides are parallel. Both pairs of sides are equal in length. The diagonals bisect each other, and the diagonals are equal in length. Okay, let's see which one's next. Next we have a rhombus, which is kind of like a squashed square. So a squashed square has 90 degrees, and it also has diagonals that are equal to each other. But when you squash the square, the diagonals are no longer equal to each other. Do they still bisect each other? Yes, they do. Okay, a rhombus is a parallelogram that has 4 sides that are equal in length. Both pairs of opposite sides are parallel. All sides are equal in length. Well, I suppose we've said that already. Both pairs of opposite angles are equal. the diagonal bisects each other at 90 degrees, and the diagonals of a rhombus bisect both pairs of opposite angles. Now that's quite interesting. It means that that has the same value as that, which has the same value as that, and that. That should be quite useful. Okay, then a square is a rhombus that hasn't been squashed, I suppose. It has the properties of a rhombus and these special properties. All interior angles are equal to 90 degrees, and there's a 90 degrees. The diagonals are all equal in length, just like the rectangle. The diagonals bisect both pairs of interior opposite angles. Now that's just like the rhombus, isn't it? But our angles aren't equal in the rhombus. Well, that one isn't equal to that one, but in a square they are equal. And they bisect each other. And there's the square, and look, there's the 90 degrees. Okay. Trapezium. Now, once again, I always think of the trapezium as the guy on the trapeze, and he's busy balancing. And the only thing that's unique about this guy on the trapeze is that the tightrope is always the same distance from the ground. So, and that's the only thing that's special about this. A trapezium is a quadrilateral with one pair of opposite sides parallel to each other. Okay, well that was quite a mouthful. We've got one last thing to look at in terms of our quadrilaterals. A kite is a quadrilateral with two pairs of adjacent sides equal, one pair of opposite angles equal, the diagonal between the equal sides bisect the other diagonals, and the diagonal between equal sides bisects the interior angles. The diagonals intersect, not insect, at 90 degrees. So there is the 90 degrees. That line is equals to that line, and that line is equals to that line. That angle is not equal to any other angle other than this angle. So those two are equal, and this one is equals to that, but these angles have not been bisected. However, the angles at A and C were bisected by the diagonals. This line is equals to this line because the diagonal that goes through from, well, the longest diagonal in this case, bisects those. Okay, grade 10s, trigonometry. Take a look at the pretty face for a while. Now, trigonometry, you'll remember that there were three ratios that were important. There was a sine, cosine, and tangent. Now, you do get those other ones, cosec and the cot and all of those, but the sine, cosine, and tan, or sine, cos, and tan, are the three that are really, really important. And they all center around a right angle triangle and the ability to be able to name the sides of the triangle and then put them in the correct relationships. Now, it has been a while since you've done trigonometry, so you need to just go back to your notes and make frantic notes on everything that you did before and practice lots of examples. This kind of stuff is actually really important for grade 11. So get it right now, and then grade 11 will be easy for you. Okay, let's take a look at a right angle triangle. So we're going to talk about the trigonometric ratios, and you'll remember that I spoke about an abbreviation, SOHCAHTOA. Why? Because sine is equals to opposite over hypotenuse. So sine of theta is equals to my opposite over hypotenuse. So what do you think cos is equals to? Well, cos of theta is equals to adjacent over hypotenuse. And tan of theta is equals to opposite over adjacent. Okay, now if we're looking from A, and that makes sense, we can just let's get this out. Sine of A is equals to the opposite value over the hypotenuse value. And cos of A is equals to the adjacent value over the hypotenuse, and tan of A is equals to the opposite over the adjacent. So it's important to always state which angle you're looking at the triangle from. Because if we had looked at it from C, then this would no longer be opposite. That would be adjacent because it's next to, and that would be opposite. Anyway, we'll go down. Special triangles. Now there are two special triangles that you need to know. There's the 45-degree triangle and there's the 30-60-degree triangle. These are very, very important. So make sure that if you haven't drawn them somewhere, you draw them now, quickly. Quick, quick, quick. You done? Oh, good, because we've got lots to do. So I'm going on to the next slide, which is functions. Now, grade 10s, functions. I love functions. Functions, they just show us what maths is about. And maths is really applied physics. Or physics is applied mathematics. So you can take a lot of what you do in maths and you can apply it to your physics. And you can draw relationships from the world, especially with things like the sine function and linking it to sound graphs and stuff like that. So it really, really is exciting stuff. With the trigonometric functions, it's pretty easy to remember. The sine function starts at 0, goes up to 1 and down to -1, and comes back to 0 again after 360 degrees. Now that's if you have just a plain old y is equals to sine theta. The period is the amount of time it takes for the graph to repeat its pattern. So once it's gone up, down, and then returned to that 0 point, it's traveled a period of 360 degrees. Its range is the amount it goes up and down on the y-axis, or the y values it covers. So in the sine function, it's going to be from -1 all the way to 1. There are no points above that or below that where the sine function is drawn. Okay, shall we take a look at some of the notes then? So, as we said just now, the period is 360 degrees. So here's my sine function, and it goes all the way to 360 degrees. The range will depend on the values of A and Q, because we might decide to move the sine function up, and then it's going to go all the way to 2 and down to 0, meaning that our range is going to be between 0 and 2. So it does depend on those. The value of A affects the amplitude of the graph. Now the amplitude of the graph is the height from the middlemost point. Okay. Now there's a lot here. So for when A is more than 1, there is a vertical stretch and the amplitude increases. For when A is a fraction, the amplitude decreases. And if you think about that, that makes sense, because if it's half sine theta, let's just go back and look. You see, there's A. If we're multiplying sine theta by half all the time, what is it going to go up to? It's only going to go up to half and down to -half. So it becomes half the size. And if A is less than 0, in other words, negative, it's going to be reflected. It's going to be upside down. Then once again, the amplitude will decrease if A is a negative fraction, but if it's a positive, or not a positive, a negative integer, it's going to increase, but there's also the reflection about the x-axis. The changing the values of Q will move the graph vertically up or down. Okay, so that means if we're going to add something to the sine function, it's going to move it up. But if we subtract, so we could say sine of theta minus 2, that means it's now going to be down there. Okay, now the cos function functions really in a very similar way, and I'm just going to draw it quickly. so we don't waste too much time. We have the cos function that goes like that. Y is equals to cos theta. Now, when it's drawn just normally, or without any changes, it has a period of 360 degrees and a range of -1 to 1. Now, if we're going to shift it up, we'll add or subtract something to it. Oh, sometimes I wonder what's going on in my head. So, cos theta plus 1, it's going to move up one space, which means that now it's at -2 and 0. The range has changed just because we moved it up. If we multiply cos by a negative, which is where this starts saying, talking about it, that means that the cos function is now going to be reflected. So it's going to be upside down. And it'll start over here at -1 and 1. But if we decide to stretch it as well, for example, y is equals to -2 cos theta, it's going to go all the way from -2 up to 2 and down again. There's the -2 and up to 2. Okay. The last thing, the tan function. Now, it's different because it has a period of 180 degrees and its asymptotes are at 90 and 270 degrees. So it's going to go like this. Let's just make the asymptote different from our axis. There's an asymptote at 90, and then we have the function drawn over there and an asymptote at 270. So the 90 to 270 indicates the period of 180 degrees because there is a difference of 180 degrees there. Because the tan function carries on going forever and ever and ever and ever and ever and ever, all the way up and all the way down, the range is forever and ever and ever. The value of A affects the steepness of each of the branches of the graph, and changing the value of Q will move the graph vertically up or down. Okay, grade 10s. Fortunately, that was the last note for now. When we come back, we're going to go through some questions quite quickly, but I know you're going to be fine. See you just now. Okay, grade 10s, now that we've gone through a whole lot of notes, we now